Hello and welcome to lecture 8. In last lecture we were discussing about velocity components and their importance for axial flow compressor. We have discussed about the velocity triangle. We started with talking about incorporating the component, that's what is called inlet guide vane, and then what is the modification in our velocity triangle. We have discussed about how you will be having different velocity triangles at different span or different location, that's what is at the midsection, at the hub as well as at the shroud. And we realize what all is the use of this velocity triangle and what is the reason why we are having our variation in blade angles, that's what is starting from hub to shroud. Let me tell you, people they are having understanding of aerodynamics of aerofoil. The understanding of fundamentals of aerofoil, that's what is applicable to this axial flow compressor, but you can realize this is what is not a two-dimensional body. Because of variation of your radius, we are having our blade that will become three-dimensional body. So the concept, that's what is applicable, but my whole flow physics in sense of understanding, in sense of aerodynamics, that's what is totally different. It has nothing to do with what aerofoil we are discussing about the wing. Okay. So now onwards when I say aerofoil, just be clear, we are talking about the aerofoil, that's what is used for axial flow fan or axial flow compressor. Then we started talking about the work done correlation, that's what is representing your case for aerodynamic work and your thermodynamic work. Okay. Now this is what we have derived, this is what we were discussing about my specific work done using my aerodynamic correlation, using my velocity triangle, that's what can be written as W, that's what is equal to U CA tan beta 1 minus tan beta 2. We have our fundamental understanding of thermodynamics, what we discussed in our last module. Okay. Now let's move ahead, what all will be the use of these relations. Okay. So what we know from our Euler's equation, my work done, if I am assuming my axial velocity to be constant, that's what is been represented by W, that's what is equal to UCA tan CW2 minus CW1. Okay. Now if I am correlating this aerodynamic work with my thermodynamic work, that's what can be represented as H02 minus H01. This is nothing but Cp T02 minus T01. This total enthalpy, that's what we can represent in sense of static enthalpy and my velocity component. So here we can write down, this is what is given by H2 plus half C2 square and this is what is H1 plus half C1 square. Okay. And if I'll be putting in this equation, that's what will be giving me correlation in sense of my peripheral speed, in sense of my whirl component and my absolute velocity. Now here in this case, if I will be using my fundamental understanding of trigonometry and if I am using my cosine rule, it says U1 by CW1, U1 into CW1, that's what is given by half C1 square plus U1 square minus V1 square. At the exit I can write down U2 into CW2, that's what is half C2 square plus U2 square minus V2 square. Okay. And if I will be putting all together, that's what is giving me my work done as half C2 square minus C1 square plus half V1 square minus V2 square. And let me assume my peripheral speed U2 and U1, that's what is equal. Okay. Now we have seen in last lecture that my U2 and U1 may not be same when I am talking about the high speed compressor, when I am talking about high pressure ratio compressors. But at this moment, in order to understand, this is what is representing my third way of work done. So first we can represent by using aerodynamic fundamentals. Second, we can discuss by using say aerodynamic work done, and this is what is representing in sense of your kinetic energy. And this is what is you already know. What we know here, if you look at, this is what is representing my relative velocity at the entry. This is what is representing my relative velocity at the exit. And what we realize, my relative velocity at the entry, that's what is larger, okay, and my relative velocity at the exit, that's what is say smaller, okay. Now if that's what is your case, you can say this is what is responsible for doing my diffusion work, okay. So you know, like your diffusion, that's what is being represented in terms of my relative velocity components. Same way, if you look at my absolute velocity with which flow is entering inside my rotor and absolute velocity with which my flow, that's what is coming out from my rotor, that's what is represented here. So here you know my absolute velocity, that's what is larger at the exit of my rotor, and my absolute velocity is lower at the entry of my rotor, and that's what is represented here. So you know, like this is what is also one of the way to understand the work done component. This is what is very important when we will be discussing about the different kind of stage configuration. We will be discussing in detail in next session, but at this moment just realize this is also one of the way to represent our compressor work. Okay. Now if we compare our aerodynamic work and thermodynamic work, it says this is what is m dot Cp T02 minus T01. This is what is representing my aerodynamic work. It is m dot U Cw2 minus Cw1. And as we have seen, this is what can be represented in sense of your absolute flow angle. That also can be represented in relative flow angle. Okay. So this is what is representing my relative flow angles, beta 1 and beta 2. Now let me compare these two equations. I can write down my stage temperature rise, that is nothing but T02 minus T01, that's what is given by UCA by Cp into 10 beta 1 minus 10 beta 2. Now here let me put this beta 1 and beta 2, we can say that's what is say delta beta. Okay, that's nothing but the change in my relative flow angle, change in my relative air angle. Okay. Now what we know, our compressor ratio or compressor pressure ratio, that's what we can represent in sense of my stage efficiency or isentropic efficiency into delta T0 divided by T01 to the power gamma over gamma minus 1. Now let me combine these two equations. In place of delta T0, I will be writing UCA by Cp into 10 beta 1 minus 10 beta 2. So here if you look at my pressure ratio, this is what is a function of all these parameters. Now this is what is very important. This is very important for us to realize, okay, how we will be getting our pressure ratio. So let me move to say our next slide. Say this is what is representing our compression ratio as we have discussed. Now let's discuss about what all we are expecting from our compressor application to aero engines. Okay. Now what all we are looking for our future engine, we are looking for compact engines. That means I want to reduce the overall size of the engine. That means if I consider I want to reduce the number of stages, that's what we are using in axial flow compressor. And we have realized when I was discussing polytropic efficiency, it says you increase the number of stages such that you will be getting higher overall efficiency. Now next, that's what is lighter weight of our engine, because that's what is directly related with your drag of the engine, drag of your aircraft, and that's what is directly related with your fuel economy. That means your pressure ratio, that's what is always a major parameter in order to design your engine. Okay. When I say I am looking for this kind of situation, it says I am looking for per stage pressure rise to be large. I am looking for per stage pressure rise to be higher. If my per stage pressure rise, that's what is higher, I can reduce the number of stages required to do particular compression. If I am reducing the number of stages, that's what is reducing my overall length and weight of the engine. That's what is my requirement. So now the thing is, based on this correlation, if you look at, it says per stage pressure rise, if I am looking to be increased. So if you look at, this is what is representing my entry temperature. So you can understand, for aero engine, since it is flying at different altitude, say ground condition, cruise condition, those conditions are different. So my T01, that's what is, you can say it is my atmospheric condition. That is not in our hand. Okay. Now if you look at here, this is what is representing my isentropic efficiency, my adiabatic efficiency, and we have realized that's what is basically depending on how many stages we are incorporating. Okay, and how good design we are doing, because this is what is basically correlating losses. Okay, so if we are able to reduce the losses, that's what is happening in my compressor, we can improve the efficiency. Okay. Next component, it says my peripheral speed. So what it says, if I am looking for per stage pressure rise to be large, I need to increase my peripheral speed. So that's what it says, in order to maximize per stage pressure ratio, increase your peripheral speed or your blade speed. Okay. Next component, if you look at, that says like my axial velocity. So what it says, if I am increasing my axial velocity, I am able to increase my pressure ratio. Okay. And as I told, this is what is representing my delta beta. Okay. That is nothing but my blade deflection angle. How I am deflecting my flow, what angle I am putting at the entry and exit, that's what will be deciding my delta beta. Okay. So it says higher fluid deflection in the rotor blades. So now you can understand what all we are looking for. We are moving towards the solution. Okay. What solution we are looking for? We want to have high per stage pressure rise. So let's discuss one by one. Suppose if I consider, say, first case, I want to increase my peripheral speed. Now when I say I want to increase my peripheral speed, we are having two options. First, that's what is, you increase the diameter of the engine or diameter of your compressor. Okay. Second, it says increase your rotational speed. So both the options seems to be easy in that sense. So let's have a look at, this is what is, say, my velocity triangle at one of the station. And as per the recommendation, if you look at, I am increasing my peripheral speed. Okay. So you can see this is what is increase of my peripheral speed. Either I can increase my rotational speed or by increasing my diameter. So what is happening here, if you look at my relative velocity component at the entry of my rotor, that's what is going to be increased. Okay. Same way, what is happening at the exit of my rotor, because I am increasing my peripheral speed, my relative velocity at the exit of my rotor also will be increasing. Now, this is what is a tricky case. Okay. What is happening? Suppose this is what I am putting my velocity component or my velocity triangle at the midsection. If I am moving towards the tip, what will happen? I will be having this V1 component to be very large. That will go in transonic or supersonic range. Okay. So what it will be doing? My flow will go supersonic near the tip region. Now as we know, our rotor, that's what is cantilever kind of configuration. So your rotor blade, that's what will be fixed on my hub, and other end, that's what is free. So in case of such situation, we will be having more chances for my structural damage to happen. It will give you problem, that's what is called flutter of my blade. Okay, that's what is, aerostructural kind of configuration. That's what people used to say aeroelasticity. That's what is a critical problem. Okay, so it says when I am having my rotational speed to be larger, it has a limitation in sense of my structural problem. Second, it says we will be having formation of shock that will be happening near the tip region. Now we realize this shock is nothing but that's what is increasing my irreversibility in the process. That's what is creating the blockage to my flow in that particular region. And if that's what is your case, what will happen? You will be having your efficiency to be lower because my losses are going to increase. Okay, so this is what is one of the plot. That's what is giving you idea how you will be deciding your entry absolute velocity. Okay, so and this is what is representing my relative Mach number. On my x-axis, that's what is representing my blade speed. So this will give some idea what all numbers you need to decide with. So here if you look at, if I will be increasing my absolute velocity, suppose say my entry is axial entry, if I am using say 200 meter per second, and if I will be moving with say increasing my blade speed, you can say my relative Mach number, that's what is going to be high. And if that's what is your case, you are having other kind of problem. Now at this moment I am saying increasing your speed, that's what is creating trouble in sense of formation of shock, and that's what is reducing your efficiency, and people they used to avoid that kind of situation. But with the development of technology, with the use of your computational tool, with sophisticated instrumentations used in your experimental part, now we are able to achieve very high pressure ratio with minimum losses by using special kind of aerofoils. Okay, those aerofoils are called transonic aerofoils. Okay, by using this transonic aerofoils, you are able to address this problem. Okay, so from beginning, if I'll be talking about all those stuffs, then you will be having confusion what all we are discussing at this moment. But just try to look at, try to understand, this is what is one of the problem. So problem is with my structure, problem is with my rotational speed, and problem that's what is with my shock formation. Okay, so it says higher rotational speed, that's what is little tricky. Now what all people they are working at this moment. Okay, so these are different engines by different companies. If you look at, this is what is representing Pratt & Whitney 4000, that's what is having overall pressure ratio of 42.8, and your thrust is roughly 435 kilonewton. Now what we are discussing here, if you look at, this is what is my fan, that's what is having pressure ratio roughly in the range of 1.4 to 1.6. This is what is say my LP spool, this is what is my HP spool. Okay, and this HP spool, that's what is connected with my HP turbine, my LP spool and fan, that's what is connected with my LP turbine. Now just look at, okay, here if you look at this stage what we are having, that's what we say LP compressor, that's what is having larger diameter. Okay, and if you look at here for HP spool, my diameter is coming to be lower. Okay, do not get confused. In order to have good look of engine, people they have done like this. No, this is what is with your fundamental understanding. What fundamental understanding? That's what is your Euler's equation. Okay, what it says, my work done or my pressure rising, that's what is a function of my peripheral speed. So if I am increasing my diameter here, I will be able to achieve high pressure ratio. Remember one thing, say your LP compressor does not mean that it is making or it is generating low pressure. HP compressor does not mean it is generating more pressure or high pressure. Okay, it may be possible that LP compressor will be generating more pressure compared to your HP compressor, but here you can see. So, in order to rotate my fan at a lower speed, okay, this spool, LP spool, that's what is rotating at the low speed, and that's the reason why this diameter is coming to be large. Now for HP spool, if you look at, my rotational speed will be larger, it will be higher, it may be more than 12,000 RPM, and for fan may be rotating around say 2500 or maybe 3000 RPM roughly. Okay, so since my rotational speed is higher, that's the reason why my diameter is going to be lower. Okay, so this is what is we need to realize in sense of engines. Now here if you look at, this is what is representing my G9X engine, and if you look at, that's what is having say thrust capacity of 600 kilonewton and pressure ratio of 60:1. Now in this case also, if you look at carefully, this is what is giving me special provision in which I will be having number of stages to be lower. Just look at here pressure ratio, that's what is in the range of 42.8, and just look at this is what is 60:1. Okay. Same way there is a other company, that's Rolls-Royce, they are working uniquely on 3-spool configuration, and if you look at carefully, my HP diameter, HP compressor diameter, that's what is lower, okay, and my number of stages are also lower. Okay, so this fan that will be rotating at the low speed, my intermediate pressure spool configuration, that's what is rotating at medium speed, and my HP spool that will be rotating at the high speed. Now this is what is representing the most recent trend, that's what is called gear turbofan engine. If you compare here, if you look at my HP compressor stages are less, okay, you can realize the reason is this is what is rotating at the high speed. Okay. Same way if you look at my LP compressor stages are also lower, that is also rotating at the high speed. Now in between, so we are having this gearbox. So this gearbox let my fan to rotate at low speed. So that's what will be improving my thrust generation capacity, my pressurizing capacity. You can understand, the larger the diameter, the more chances the formation of shock near the tip region, mainly for your entry at the fan. Okay, so this is what we need to realize. So now using the fundamentals, what all we are discussing, say using your fundamental equation, by increasing your peripheral speed, you are able to increase your per stage pressure ratio, you are able to reduce your number of stages. Okay. Now let me move to the next, say next option what we are having, it is increase your axial velocity. So here in this case, if I look at, say this is what is say my original velocity triangle, let me increase my axial velocity. If my peripheral speed, that's what is say same, I will be having my V1, you can see V1 dash, that's what is my relative velocity component, that will be coming to be large. Okay. Same way if I will be putting say at the exit, I will be having my axial velocity to be large. If my peripheral speed is same, I will be having this kind of configuration. Now here also if you look at carefully, this is what is representing my beta 1 dash, that's what is lower than my beta 1, and here this is what is beta 2 dash, that's what is lower than that of my beta 2. Now again the situation is same as what we have discussed for your high speed configuration. What happens? You will be having your flow to be supersonic, or it will go in transonic region at particular radius. Issue, that's what is same, you will be having formation of shock, it will give the blockage to your flow, and that's what is reducing your efficiency. Okay. Now the question is like this all are the limitations, and as I told, people they try to come out from these difficulties of formation of shock. Now the challenge that's what is come is how do we increase our axial velocity. Just realize this axial velocity, that's what is a responsible parameter for my mass flow rate. Okay, so what it says, in order to have your axial velocity to be large, you need higher mass flow rate per frontal area. Okay, frontal area in the sense my air that will be sucked from my front side or from my, say for high bypass or low bypass ratio engine, my air that will be sucked from the entry. Even for turbojet also it will be entering from your entry case, or say my diffusing passage. Okay. Now what happens? This is what is creating the trouble. Suppose if I am talking about, say, turbojet engine and turbofan engine, we are having some constraints in sense of diameter. Okay, and this diameter, that's what will be going to be large. So many times when I am talking about, say, my application to aero engines, okay, especially for military configuration where my diameter, it's a constraint. When my diameter is a constraint, I cannot go with increasing my frontal area. Okay, so logic of increasing your axial velocity with limited frontal area, that's what is tricky. Okay, now what hint it is giving? You are having option for high bypass ratio engine. That's what we are using for our commercial aircraft. You can go with high bypass ratio or very high bypass ratio kind of engine. That's what is called ultra high bypass ratio engines. So by 2025, we will be having future engines, they are ultra high bypass ratio engine. So you can understand, people with maturity of technology, with understanding, fundamental understanding of what all we are learning, they are being implemented. Okay, so you need to be very thorough with all these aspects. Once you are having your fundamentals to be clear, you can think in an innovative way, just find the solution with the problem. Okay, now let me go with, say, our next configuration. What it says, like high fluid deflection in the rotor blade. So here if you look at, this is what is, suppose if I say I am having my original blade. Okay, now it says I need to have higher deflection. So I have modified my aerofoil in order to accommodate my beta beta, that's what is beta 1 minus beta 2. If you look at this case, I will be having my aerofoils that will be changing like this. It says it's cambered aerofoil, highly cambered aerofoil compared to these aerofoils. Okay, so this is what is, say, my rotor blade. Okay, so if I'll be putting my, say, velocity triangle here, this is what is my configuration. That's what is, say, my entry velocity. It's, say, my V1 and my angle is beta 1. Now what happens? Say at the exit, my relative velocity component, that will be going to be lower. Just look at, if you compare side by side, you will realize, say here what V2 we are getting and what V2 we are getting, this velocity at the exit of my rotor, that's what is coming to be lower. Okay, and my beta 2 angle also is coming to be lower. It says I am having my delta beta to be large. Okay, now what happens? What flow, that's what will be coming out. At one side it is reducing my relative velocity, but on other side it is increasing my absolute velocity. Now the challenge, that's what has come, is in sense of your next component, that's what we say as an absolute velocity component. That's what is entering in my stator. So here if I look at, I am looking for my exit, that's what is, say, axial. So we will be having our stator also as highly cambered blade. Okay, so this blade, that's what is cambered blade, this blade is also cambered blade. You can say this is what is my rotor and this is what is my stator. Now the challenge that what has come is with your aerodynamics. What it says, we are working under adverse pressure gradient. My entry pressure is lower, my exit pressure is higher. When my flow, that's what is acting under adverse pressure gradient, we have more chances for my flow to get separated. So like if I consider, this is what is a region where I will be having more chances for my flow separation to happen. It will not limited only with the rotor. It may happen that you will be having your flow separation. That's what will be happening in my stator. Okay. So, one of the simulation what we have done in this, like this is what is representing my streamlines, and you can clearly see for the stator we are having the flow separation. That's what has happened from the stator blade. So, going with larger delta beta, that's what is very challenging. So, the train, that's what is going on, it is to make per stage pressure rise to be large using this kind of configuration by changing my delta beta to be large. This is what is very challenging. Okay. People, they are working on this aspect. At IIT Kharagpur also we have explored designing high pressure ratio low speed compressor. So, this is what is one of the simulation what we have done. So, you can see this is what is the problem. It may happen that your flow separation that will be happening from your suction surface. Many chances it may happen you will be having your flow separation that will be happening even from your pressure surface. Okay. So, to achieve high pressure ratio, per stage pressure ratio for axial flow compressor, that's what is always very challenging part. Okay. And today we have discussed about different possibilities. One of the possibility we have discussed, that's what is in sense of increasing your peripheral speed. Second option we have opted, that's what is by increasing your axial velocity. And third option we have discussed, that's what is by increasing your flow deflection or making your blade to be highly twisted or highly cambered. Thank you very much for your attention. We will be moving forward in the next lecture. This all will be giving you very much fundamental idea what we say in sense of design of axial flow compressor. With all these fundamentals, if you will be moving ahead, you will be having detailed maturity what we say in sense of design. So, design of axial flow compressor always is very challenging, and that's the reason why whole lot of research and development activity, that's what is going on throughout the world for the development and design of this axial flow compressors. Thank you very much.